Welcome, and thank you everyone for joining us tonight for the first of our AFI SOFA seminar series. Some of you may be aware our initial plans for the annual national conference this year was to co-host with Casting Technologies New Zealand. COVID-19 and travel bans saw these plans cancelled quickly, but not to be deterred, AFI Vic decided to try and put on a national conference ourselves. So we arranged a venue in Melbourne, but unfortunately, COVID outbreaks continued to thwart our efforts, and stage 4 lockdowns in Melbourne meant that we were not able to do that. So, being Foundry people, by our very nature, we are problem solvers, and AFI Vic was determined to continue to present a series of presentations by guest speakers, and so came about the SOFA seminar series for 2020. This is 4 fortnightly presentations from our exceptional guest speakers, the first of which tonight is Dr. Roger Lumley. As Gary mentioned, everyone is now on mute, so I appreciate that, and if you keep your video off, that will stop any background noise or any interference that we may get throughout the presentation. And finally, question and answer session, the question bubble on the bottom of your screen. If you do have questions, please type those in throughout the presentation, and Gary will be organising and presenting those to us at the end of the session. So tonight, Roger, many of you will know Roger. Roger has over 25 years of experience in materials, science, engineering, manufacturing and research, and project management. Roger has a science degree in metallurgy, a PhD in materials science and engineering, a higher doctorate in engineering. Roger has authored over 100 technological publications, including patents, journals, and conference papers. Roger has even authored a book. Roger is a fellow of the Institute of Engineers Australia, and Roger is an elected fellow of the Australian Academy of Technological Sciences and Engineering. Roger was also recently elected to the position of National President of Materials Australia. Tonight, thank you, Roger. He will be presenting to us his experiences on the development of thin wall cast Invar for satellite applications.
Great. Well, thank you very much, Amber. I'll just share my screen now, and hopefully we should be able to get everything on the way. Okay. All right. Now, you should be able to see everything, I believe.
All good, Roger.
Yep. All right. Awesome. Yep. Okay. So, well, thank you very much for coming along to this presentation this evening. My role is as Senior Technical Specialist with AW Bell. We're a foundry in Dandenong South in Victoria, with a focus on aerospace, defence and biomedical products. We're AS 9100 certified foundry, and we have the main business is foundry. We have production machining, and we also have machinery building. We part of our business is building foundry equipment, so grinders and cut-off wheels and things like that. But what I'm going to talk to you tonight about is specifically information related to a project that was done in conjunction with Defence Materials Technology Centre. It was a collaboration between AW Bell, La Trobe University, CSIRO and DMTC, and our part of it specifically was associated with casting Invar for cube satellites specifically. So just to give you a quick company overview of AW Bell, we're a global supplier of complex metal parts with high mechanical properties to aerospace, defence, space and biomedical industries. And our vision is to be the most innovative and customer-focused supplier of quality casting solutions globally. Very proud to say that the Joint Strike Fighter program is still the major part of the business that we're currently doing, and that's been a fantastic opportunity and a great opportunity for us all round. So On to today's presentation. What I'm going to talk to you about, and this is reasonably informal. I mean, basically, I'm going to tell you basically what we've done in this project. It was a very, very interesting project to do. It was something really quite new for us. I mean, we in AW Bell we cast everything you can melt in air. So everything from all your non-ferrous materials you can cast in air: cobalt, nickel, cast irons, steels of every description you can possibly think of, but never really looked at anything quite like Invar. Today I'm going to talk to you about what CubeSats are and why they're important to us, thermal drift of sensors, and why do you choose Invar? Why is Invar important for satellites and for sensors? I'll talk about the Invar effect, the scope of the project, give you a brief overview of investment casting, just in case there's anyone in the audience who doesn't know what investment casting is, because I know this talk was advertised fairly widely. I'll talk a little bit about how thin and the alloys that we looked at, and some of the reasons why we went down the path we did in looking at different wall thicknesses. I'll talk about some of the issues we actually did find, especially related to hot tearing. It turns out that hot tearing was one of the major issues that we came up against. Show typical microstructures, talk about effective alloying elements, fluidity testing, and then go on to what we actually did in the satellite chassis production. So cube satellites. Now, what a cube satellite is, it's defined as being of dimensions that are in multiples of 100 millimeters. So they're quite small. You know, basically you can hold up a ruler like this. You know, that's a 30 centimeter ruler, 300 millimeter ruler. That's basically the length dimension of most satellite or cube satellites, and then multiples of 100. So they're called cube satellites because they're cubes of 10 centimeters. And quite typically, CubeSats can be employed either by themselves or they may be employed in constellations. If they are employed in constellations, it means that you've got a whole lot of them over a very large area, which creates an array. And that's very, very useful if you want to get a really, really good look at everything. So the cost to build and launch a CubeSat is one of the big attractions to them. Generally, it's considered to be around about $20,000 to build and launch a Cube satellite. Most of that, of course, is associated with the launch part of it. The build of a Cube satellite is actually quite cheap. With the technology that goes into Cube satellites really taking off at an exponential rate, the small satellite market, that is Cube satellites of around about the dimensions that I mentioned, have a market estimated around about $23 billion globally over the next 10 years. So, you know, it's a big emerging marketplace. And certainly there are both, there are a whole lot of different applications for them. We did this work under the Defence Materials Technology Centre because Australian Defence Force were interested in what opportunities might be available to them in looking at satellites, and very small satellites in particular. So thermal drift of sensors in space is actually quite a significant issue, and it's actually a very, very big topic. I never really realised how much of a big issue it was until I started looking into it. And it really is the case that sensors require very high precision, or they have to be continually adjusted to account for changes in dimensions with temperature. So the thermal drift is defined as the changes in normal operational behaviour of a device due to changes in ambient temperature. This thermal drift is caused by internal heating of equipment during normal operation or by changes in external ambient temperature. And really what it comes down to is parts of a satellite face the sun, and they can be operating up around 150 degrees Celsius. Others are facing space, so you know they can be minus 150 degrees Celsius. It really depends on what the orbit of the satellite is. Never realised how much of a satellite is actually a cooling system. It's actually quite substantial. So being able to overcome some of the issues with thermal drift means that you can go to these miniaturizations. So the cube satellite model, or what's also called nanosatellites, where you're sort of talking about even smaller, again, sort of this size. One of the big advantages once you get to the very small sizes, as the price goes down, and and you can therefore launch more of them into a constellation scenario. So why Invar? So Invar is a very, very interesting material. Invar is basically, well, it is iron 36% nickel. It has a minimal coefficient of thermal expansion over a very wide temperature range that minimises the thermal drift for sensors and components. Now, it was actually discovered invented in 1896 by Charles Edouard Guillaume at the International Bureau of Weights and Measures in Paris. Now, of course, history says that they found it on purpose because they were looking for something that had very, very low coefficient of thermal expansion. But of course, we all know that quite often invention and discovery are not necessarily the same thing. But one of the things I found about it, even though the material has been around for quite some time, and it is becoming more important today for a range of different applications, the amount of information on actually casting Invar parts was very, very limited. I found continual references to a Metals Handbook from the 1948 edition. I couldn't find a copy of it. I actually eventually found a copy that I could buy that was an ex-library book, and it had a small amount of information from that time frame. And then there's also a small amount of information that came from Howmet, which was put out in some Howmet publications in the mid-1980s, which was specific to investment casting. So there was an extremely small amount of information I could find. There was some information that I was able to get from people that I spoke to who had their own experiences with it, but they couldn't share written information with me because of the nature of the projects that worked on. But interestingly, today the major use of cast Invar is in carbon fibre tooling, especially for aerospace products. And just to give you an example, this is a picture of machining of Invar for carbon fibre tooling, and this is a picture which has originated from Coast Composites Incorporated Tooling Division. Coast Composites actually manufacture wing sections for a very vast array of commercial airliners, Boeing, Airbus, and companies all over the world. And basically, my understanding of it is that the big Invar foundries actually cast these very, very large pieces, which are then mounted onto a frame, which actually is Invar as well. They machine the shape of the wing piece out of it, and that then becomes the carbon fibre tooling. Now, the big importance of it, of course, is the fact that it doesn't move around with temperature, and that's why it's so desirable for tooling applications. So this just puts it in a little bit of context as to where most of the use of Invar has gone today. And because as carbon fibre grows in aerospace, Invar use is growing as well. So that's a little bit of an aside. It's not what I'm talking about, but I just wanted to put it in context of this is where a lot of the technology currently resides. And Boeing has their own specification for this kind of thing, which is a little bit different, which I'll talk about a little bit further on. So the Invar effect, and this is a picture which is published in, I believe, in the 1970s. It appears in a book that was specifically written about Invar. And what you can see here on the x-axis is the percent nickel in iron, and that's weight percent nickel in iron, and the y-axis is the coefficient of thermal expansion. And what you see is that the coefficient of thermal expansion drops to not quite zero, but nearly zero at very, very close to 36% nickel. It's quite an extraordinary effect. Basically, you have on either side of 36% nickel, you have what tends towards normal coefficient of thermal expansion, but right on this particular concentration, you get, and a little bit either side of it, you tend to get very, very low coefficient of thermal expansion. So this is what's more commonly termed the Invar effect, and there's some materials display it, but nowhere near as significantly as the iron 36% nickel material. So the project scope, now this was part of the project 11.62 for the high altitude sensor systems, and the greater project name was Advanced Manufacture of CubeSat Components, and it was a collaboration between DMTC as the body who had oversight of what we're doing, University of New South Wales, who provided designs for the structures that we built, and some of the hardware that went inside, CSIRO, who were looking at 3D printing of some titanium parts, which went internally into the structure, La Trobe University, and outside AW Bell. So our part of the project was to evaluate the feasibility of manufacturing thin wall Invar from investment castings. So what we did was assess alloys based on their castability, coefficient of thermal expansion, and propensity to form defects. And a particular focus was on optimizing the thermal expansion over the temperature range of -150 to +150 Celsius, therefore making it suitable for satellite components. So the investment casting process, I won't spend too much time on this because I'm assuming that most of the people here actually know a little bit about it. It's essentially the lost wax process where we start with injection of a wax part. We then take the wax component, we put it onto a tree. We put a series of prime coat, backup coats and stucco onto the tree, onto the wax tree. Produce a ceramic shell where we then take it, after the ceramic shell is produced, we remove all the wax from it in an autoclaving process, preheat and fire the shell mold, cast metal into it, and then we have the tree that comes out. At the end, we knock off the shell, the ceramic shell that's left behind, and cut off the parts and fettle it and finish everything. And you can see the steps on the middle picture on the screen here. On the right-hand side is some pictures of some actual parts, and these are a swirler. They're not a propeller. They actually only move air, and you can see the model with the wax and the cup on it at the top, and then onto casting it in the middle, and then final part upside down at the bottom. So it's a reasonably straightforward process. It is the lost wax process is very, very old. One of the oldest casting methods known to man, but today it has become quite high tech in a lot of the ways that it's used. So where we started with this project was looking at how thin you could actually go, and what we did was we were using an SLA printer to print the shapes that we were going to do. So we weren't using wax preforms; we were using SLA plastic preforms. We printed these small boxes, and these are in dimensions of around about 10 centimeters by 10 centimeters by 10 centimeters, and they have 5 different wall thicknesses. Now, it's not a fantastic design for down sprue, but it sort of had some of the characteristics that we wanted to be able to look at. And what you have here is wall thicknesses that vary between about the target was between 0.8 and 6.2 millimeters. And we didn't quite get to 0.8 millimeters because when you print at 0.8, it actually came out a little bit thicker just because of the fact that things do move around. But we were able to get down to 1 millimeter where we were targeting the very thinnest walls. And so you can see the model of the parts, the trial parts on the tree up in the top left corner, actually on the tree being manufactured in the bottom left, casting in the middle where the shell's been preheated at 1,000 degrees and the metal temperature was 1660. And on the right-hand side is one of the finished results. So what we looked at with this was the influence of carbon, manganese, silicon, chrome, and molybdenum on castability. Knowing that carbon, manganese, and silicon all improve thin wall filling. A little bit of chrome was kept in there, mostly for oxidation protection. Even 0.1% chrome can give you some reasonable protection in your material, and it tends to change the amount of slag-forming oxides that you have to deal with along the way. So the effect of various elements on the mean coefficient of thermal expansion, you can see here that silicon, manganese, chrome, and copper are all quite have negative effects on the coefficient of thermal expansion. Cobalt is generally considered to be 0. We did not add cobalt into these alloys that we looked at, the purpose being that cobalt is fantastic over temperature ranges of, say, room temperature upwards, but not so useful if you're going down to cryogenic or very cold temperatures, -150 thereabouts. It starts to not have a positive effect at those very low temperatures. So we left cobalt out on purpose. So the 10 alloys that were evaluated in the first round of testing, you can see here, we maintained between around about close to 35% up to around 36% nickel. Now these were all air melted, I would say, as well. The pour temperature was 1660. The shell temperature was 1,000, as already mentioned. And what you can see here is the variations that we made. We had varying carbon contents, silicon contents, manganese contents. We mostly tried to keep the molybdenum and chromium fairly standard. One of the reasons why we went for the compositions that we did, we found that there was an ISO specification for an Invar type alloy called GX3 nickel 36, which is from the ISO specification 19960. Now the molybdenum in there has some very interesting effects to it. It doesn't have a very severe effect on some of the other characteristics of the material. So we basically just kept that as a fairly standard sort of level around about the 0.7 to 0.9%, because moly does have some positive impacts on the outcomes that you achieve. So this was the starting 10 alloys. At the bottom was a Boeing specification material, which was a wrought version of Invar, and this was provided by Miranda Engineering over in Moorabbin. Now, Miranda, of course, do a lot of aerospace products and a lot of tooling for carbon fibre, so they were able to supply me with a sample. And so I was able to do comparisons against the Boeing specification material, which was really very, very useful. So, okay, so these are the 10 alloys that we manufactured, starting at shot temperature 1000, melt 1660. Basically, we're going down to very, very thin wall thicknesses, so everything's really at the hot end of what you do for investment casting. So the design of experiment was that alloy 1, 2, and 3 would show the effect of carbon. Alloy 2, 4, 5, and 6 would show the effect of silicon. Alloy 7 and 8 would show the effect of manganese when silicon was about 1.5%. Alloy 5, 9, and 10 would show the effect of manganese when silicon was greater than or equal to 2%. And then alloy 11, as already mentioned, was a commercially available wrought Invar according to the Boeing specification. So one of the things that we found was that in a number of these alloys, hot tearing was a real problem. This particular one is number 6, which was the 9th worst rated one. And you can see the hot tear that runs through the part here. This has been, it's had the shell removed off of it. It's not been sandblasted or shot blasted or anything like that because I wanted to actually capture the hot tears. There's a hot tear over on the left-hand side here, and there's more hot tearing here through on the right-hand side. Now this is the thickest wall, and generally when hot tears did appear, they appeared on the thickest wall. Of course, there's gates behind them on the 4 corners. And so it's no real coincidence that we saw this issue. But generally, when we did see tearing, it was not on the thin walls. It was generally on the thicker sections. And hot tearing, of course, there's a lot of microstructural reasons behind it. And but most of all, one of the very important things associated with it is the issue of constraint and where your constraint points are. So, of course, a thick wall with fairly heavy constraint points around around that area did cause some issues. But what was really, really nice was that alloys 1, 2, and 3 showed little to no hot tearing at all. And of course, the big positive out of that was that alloy 1 was actually in specification for the ISO alloy and also showed no hot tearing. So, you know, that was a really, really nice result to be able to achieve. Now, just going back to the earlier slide where I talked about the effect of chemistry, if you remember back, alloy 1, 2, and 3 were to investigate the role of carbon. So we can also say that the carbon content actually had very minimal effect on the hot tearing. It was the other elements, the silicon and manganese, that were especially problematic for this issue. And so we were able to identify pretty quickly that silicon and manganese were the culprits in this issue. Now, I did mention that not all alloys showed this problem, and this is an example of one of the ones that did not show it. I actually have this part sitting in front of me at the moment. So if anyone wants to have a look at it, I can put it up to the screen later on. We're going to talk about it in a little bit more detail. The frame around the outside of it that you see here is there purely for structural purposes. It's not there to feed it. Basically, when you are casting down around 1 millimeter in investment castings, you have to be very, very careful that you constrain things so they don't move around too much, or basically you try to cut stuff off and it starts to bend and move all over the place, and then you have a different problem to deal with. So so this ring is only there to stiffen up the outside of it to hold it all in position while we cast it. So you can see the part there. You have the very thin wall over here around about 1 millimetre, and then the back wall being around about 6 millimetres. So what this did tell us was that we could cast down to these very thin wall thicknesses in this material. But one of the things that we did notice as well, and there's an example here, there's a little fin over on the side here where the shell was cracked, and there's another one over here. Basically, wherever there was a shell crack, metal filled it. You know, at the temperatures that we're using, we were actually filling these very, very fine fins. So it did tend to suggest that, well, maybe because we do know we have a problem with hot tearing, maybe we can do something about it and drop our temperatures a bit. So that became a focus of part of the next stage of the experiments. Now, one of the things that I do have to mention about the Invar material, it has a very, very interesting solidification behaviour. It seems to have, when you look at the microstructure, and you can see this is a picture on the right-hand side of alloy 1, it's got a reasonably coarse dendritic structure. There's various small bits and pieces in the microstructure which are residue from the fact that we are air melting this material. We use an argon purge throughout melting, but you know, there is still small oxides that you can see. They the way it's been etched does show these quite clearly in the microstructure, in the interdendritic regions in particular. Now, one of the things that becomes quite clear about Invar is that it does not have a two-phase solid plus liquid range while you're going through the solidification process. You're going from liquid directly to austenite. So basically, as soon as you don't go through liquid goes to solid plus liquid goes to solid, you go liquid goes to solid in the same way that a pure material does. Now, this is a very interesting thing because, of course, there's a lot that's been written about the mushy zone inside materials and the contribution of mushy zones to tearing. Now, this is a little bit different because we can sort of look at this without that two-phase region. We can say, okay, well, it starts solidifying and we're only driven by temperature rather than phase. You know, so the outside solidifiers first, you have like this onion skin effect, much the same way as aluminium bronze does. And then it moves forward to the inside. So this was an interesting thing because the background of the hot tearing becomes a little bit more complex, and it's still something that I'm working on. But you know, it is very, very important to make the note that it does go through this direct solidification, direct from liquid through to solid. And when we look at the thermal analysis of the material, we can see that, well, the thermal arrest is very, very similar to a pure material. So what you're seeing here is this is a thermal analysis rig from Heraeus Electronite. That only cost you about $200 or so. You can get set up to do thermal analysis of steel for under $1,000. All you need is a data logger and a thermal analysis rig. These setups are absolutely fantastic. If you are casting steel or anything high temperature and you are not doing thermal analysis, you absolutely should be. It literally costs you a cup costs you about $2 a piece, and the amount of information you get out of it is absolutely extraordinary. So what you're seeing on the plot here is while it's heating up, and then when it reaches its maximum temperature, and then it starts cooling back down again. You can see that probably because it's not purely iron and nickel, you can see that there is a little kick just before the start of the main thermal arrest. But it's very, very flat, quite consistent with something that is close to a pure material, but of course it's not pure because it's got very, very high alloying content in it. So the thermal analysis is very consistent with the phase diagram. It tells us a lot about it. It does tell us that we are starting to kick off solidification around about the 1440 to 1445 range. And it stays pretty constant through the thermal arrest until it finishes. Now, depending on how you interpret the tail end of a thermal analysis diagram, you could probably say, well, once it starts getting back to a linearity here is pretty much when you're finishing. So it's not completely flat because it doesn't have a very straight angle on this edge, but it's getting pretty close to behaving like a pure material. So samples that were cast together with the boxes that I showed you before were heat treated prior to machining and thermal expansion testing. The heat treatment was done in accordance with the ISO standard. Now, the specification here is just straight out of the ISO standard. We chose parameters inside of that, and it's pretty straightforward what you need to do. There's nothing special about it. And then thermal expansion testing we had done by the Thermophysical Properties Research Laboratory at Purdue University in the States. They're extremely well set up for doing thermal expansion testing, thermal conductivity testing, a whole range of things. And basically all we had to do is machine our samples, and our machine shop did a great job in producing the samples for me, and we sent them off and had them tested. So what you see here is the effect of carbon. Now there's three curves that are shown here, and I'll just run you through what you're seeing on the curve first. So basically what you're seeing is the thermal expansion here. It's given as meters per meter. So basically you're seeing the thermal expansion as a function of temperature. And then you see where it starts to it goes through an inflection and starts to kick up again. Now, from this, of course, the coefficient of thermal expansion is a per degrees number. So, but what you see here is, well, how much is the thing actually moving as I change temperature from, say, low temperature up to high temperature? And you can see here, this is looking pretty good, because we're from minus 150 to about plus 150. We've got very, very little change over the whole range of what we're looking at. So, this is very, very promising. One of the things that was perhaps not expected, because all of the literature tends to say that carbon is a deleterious element here, we actually found that as we went from about 0.02% carbon up to about 0.1% carbon, the result actually got a little bit better. Now, this is not entirely expected, but the results were what they were, and so we saw this slight improvement as carbon went up. The important temperatures that we look at here are the inflection point, which is basically you draw a straight line off the lower part of the curve and a straight line off the top part of the curve. And this is generally considered to be your inflection point, where the behavior is starting to be lost or is lost. And then the Curie temperature. Now, the Curie temperature is basically the point at which it deviates from linearity, where I'm pointing to with the arrow here. And that's, there's a lot of different ways of measuring the Curie temperature. You can approximate it based on these curves, and approximation is all you really need, because what the Curie temperature actually is it's related to the magnetism of the material. This is outside of the temperature range that we're interested in, so it's not really, and the magnetism of the material isn't necessarily a problem for us. So, but what we're interested in is all of this low temperature behavior up to the inflection point. So that's the effect of carbon. Then the effect of silicon. Now, you can see that as we add silicon here, we still have an Invar effect going on down at low temperature, but as you go up in silicon content, you're getting less and less and less effect of this low thermal expansion down here. So now alloy 2 was the one that was showed on the previous chart, and you can see that as we go from the lowest silicon contents up to the highest, it doesn't work for us at all. Now, silicon does improve fluidity of the metal, but it doesn't help at all in terms of the thermal expansion coefficient. It also, as I was alluding to before, of course, that it doesn't help in terms of the hot tearing either. So keeping silicon very, very low is certainly advantageous. Manganese has a similar effect to silicon, although not quite as severe. I've only put two of the curves here, but you can see the general trend of it is that as manganese is increased, the thermal expansion gets worse. The point of inflection moves to a lower temperature, and things basically, it's not the direction you really want to head in, unless you really need to. And when I say unless you really need to, I'll get to reasons why you might add some of these things back in later on. So the best cast results are shown here, alloy 1 and alloy 3 versus alloy 11. Now, alloy 11 was the wrought Boeing specification material, which I had tested together with the cast material. And you can see we actually performed pretty well in comparison. The cast material, alloy 1 and alloy 3, were not bad, especially, again, over the range of -150 to +150. And the alloy 1 actually outperformed the wrought material because the wrought material actually goes down, it dips off more down at these low temperatures than the cast material did. So that was a very, very encouraging result, definitely. And now the offset in the wrought material off to the right-hand side, we we believe we knew why that was, and we proved it later on as to why it was. And basically, it's simply that the wrought material had a higher nickel content. So it had around about 38% nickel. We were working around 36%. And basically the reason why the Boeing material has this higher nickel content in it, or higher nickel specification, is because they need to operate over a different temperature range than what we're targeting. So say, for example, temperatures up to 250 degrees are very, very important for what they were looking at in terms of the carbon fiber tooling. Anyway, this is quite an encouraging result for sure. And the coefficient of thermal expansion that you can see here, this is just actually the numbers. So we're looking at the coefficient of thermal expansion between 20 and 100 degrees Celsius, and this is quite often how it's referred to in literature. And then minus 150 to plus 150, which is what we're interested in. Now you can see between 20 and 100 degrees Celsius, we're around about, on our preferred alloys, these ones here, you're around about that 2.3 mark, and that compares to the wrought material at about 1.8. But then when we look at the minus 150 to plus 150, especially alloy 1, which was the specification that was correct for the ISO alloy, coming in around about 2.1, actually outperformed the wrought material over the same temperature range. So this was extremely encouraging. And really tended to suggest, well, we'd actually done it. We'd managed to find something that would achieve the correct sorts of thermal expansions, and it was going to be castable as well. So we found that the inflection temperature was reasonable, up around 195 degrees, and the Curie temperature, or estimated Curie temperature, around 309 degrees Celsius. We looked at this a little bit further. And made some, did move towards a second set of experiments. But one of the things I did want to point out here was these two results. Now, these were from alloys that were not the best alloys in terms of coefficient of thermal expansion, and possibly not the best in terms of some of the issues we came up against with hot tearing. But what these do have is the same coefficient of thermal expansion as borosilicate glass in the case of this one around about 3, and single crystal sapphire. Now, when you say, well, why is that important? Well, basically, when you have something which has got sensors in it, you need to have windows for the sensors to look out of and go through. So there's quite often there's a requirement that your window and your material holding the window actually has to have the same coefficient of thermal expansion. So what this tended to suggest to us was that, well, if we didn't need the absolute minimum, we could actually tailor the coefficient of thermal expansion to match the window material quite well if need be. So that was also an interesting outcome. So the stage 2 trials, and so this is looking at some effects of temperature and fluidity. Now, of course, one of the things that we want to do with casting, we want to cast it as cold as possible to get a good result. This is one of the fundamental things of casting. You don't go too hot, but you've got to be fluid enough to fill your mold. So looked at the effect of nickel on the coefficient of thermal expansion, and this was based around suspicions that the result that was being seen in the Boeing specification alloy were associated with the nickel content. Some mechanical properties, that are just standard tensile properties, and then moving on to demonstrate production capability, and also welding. Now, we actually, as part of this whole project, we did a complete set of preliminary qualification records, weld procedure specifications, the whole lot for how you weld Invar, because of course one of the things that you need to be able to do is that, well, we don't like to admit that we weld our castings, but you always have to know how to do it. It's as simple as that. It's a good idea to know how to do repairs if you need to. So we developed all the methods for doing welding. I'm not going to talk about welding today at all. That's probably a topic for another talk. Basically, so these top 4 are the ones that I'll continue talking about right away. So fluidity was a major unknown, we knew that we had to have high fluidity to get to these very thin wall thicknesses, but we had this issue with hot tearing, so we had to go to as cold as possible to achieve good fluidity. Now, what you see here is a very crude fluidity test, and a gentleman named Maurice Murray, that many of you will know, suggested this to me many years ago. He said, if you want to do a quick fluidity test, just get a piece of angle line, paint it with some foundry paint, put it on an angle of around about 20 degrees or so, and pour metal into it and see what it does. That's what we're set up for here. That's just actually a cinder pig from one of our furnaces with a bit of Rio bar on the top of it, and then we have the angle iron that's in here. Now, as long as you don't move the angle iron, your results are comparable. And there's nothing particularly quantitative about doing this, but it's very, very cheap, easy to do. It costs you nothing to set it up, and you get a good result. So I did video this, so you get some idea about what's being done. Okay, so that's about 5 seconds in that one it took to run down there. Now just run it again. You need to watch the metal as it goes. Oops, I need to go back. You need to watch the metal as it's running down. And it's very, very fast the way it goes down the angle. Now, if I take that to about 1/3 the speed, so you slow it right down, you get a completely different view of what it's doing. And you also get a feel for how fast it's actually traveling. Basically, it's moving incredibly quickly under these conditions. So basically, using this test, you're able to get a very, very good feel for, is my material likely to fill my mold or not? So what you do with this, of course, is that you do this test, you run it at different temperatures, and you can see the different temperatures that were examined here between 1520, 1540, 1560, and 1590 degrees Celsius. And you do it, you take the piece off and you measure it. You can put a tape measure against it and get a measurement of it. And you start to see that, well, 1520, it flowed about halfway down, 1540 went most of the way down, 1560 and 1590 are fairly similar, but then when you actually look at the characteristics of the material, you can see that the one at 1560 is pretty chunky. The one at 1590 was almost like foil. It just ran incredibly quickly, and this is the one that was shown in the video that was running so fast. So basically, whereas we started our testing at our initial estimate was at 1660 degrees Celsius. We actually found that by doing this, we could drop down to 1590 and still get extremely high fluidity in the material. Now, this was a little bit unexpected because I sort of thought, well, this is iron and nickel, not much else. I didn't really expect it to have this very high fluidity. There are some reasons for this that I'm not going to talk about tonight, but at the end of the day, we were able to achieve an incredibly high fluidity at a melt temperature of 1590 degrees. So being able to reduce the temperature by 70 degrees Celsius, of course, meant that we were able to minimize the risk of hot tearing when we started to go to more complex structures. So the effective nickel was looked at next, and so we were looking at a number of different alloys here. 6 different materials were looked at, where we were looking at nickel contents up to around 40%. So keeping everything else pretty constant. And again, this is still air melting. Nothing done in the vacuum or anything like that. Using argon purge through melting. So we have here we have alloy 16 around 40% nickel. Maintaining around 36% in a few of these materials, and around 37 to 38% in some of them as well. But then carbon kept it around about 0.02 as well as we could. Silicon, keep it pretty low. Manganese, keep it below a sensible level. And the moly's still in there. A little bit of chrome, of course, as mentioned earlier. Sulfur, of course, very, very low. Phosphorus, very low as well. So we're basically, these are the different trials that ran through to look at the effect of nickel. And this summarizes the result very, very nicely. So as we go up in nickel content, we're going from the green curve to the red curve to the blue curve, which is completely in line with what we saw for the wrought material. Now, the green curve is very, very similar to alloy 1. It is actually in specification for the alloy 1 that I showed you earlier, the GX3 nickel 36 material, and the blue one is not that different from the Boeing specification. So you see exactly the same trend. Able to prove out that yes, nickel does influence the curve in this way. But the interesting thing is that the red and the blue curve here would go very, very close to meeting the specification for the Boeing tooling as well. So that was a very interesting outcome to be able to achieve. Now, mechanical properties, this is the average tensile properties of the Invar containing the different levels of nickel. They're all basically the same. You know, I wouldn't say there's any great variation here. Generally for Invar, you're going to see around about 280 to 300 megapascals proof strength, around 400 to 430 megapascals tensile strength, and around about 30 to 40% elongation. Now, I mean, I know for those of us who work in aluminium, we're not always used to seeing very high elongations around 30 to 40%. But sure enough, if you can achieve these kinds of low strength values, you do get this sort of high elongation. And I would say if you plan on manufacturing Invar at all, the fact that it's got these tensile properties make cutting with abrasive wheels very, very tricky. It tends to glue up your abrasive wheels very, very quickly, and things get pretty warm pretty quickly. So the chassis production, now this was the CAD that we were provided with, and so this is the CAD file that University of New South Wales passed on to us. Now, not all of these features were structurally important, but they were there basically because they said, well, you know, you want to be able to cast complex things at thin wall thicknesses, so here it is. And now, in particular, these crosses here, the sections through the middle here were 1 millimeter. And you know, the pathways to get metal to those not particularly great. So it was a very complex casting to be able to make. So we went down the path. So we started with the CAD file, and we went down the path of building these on our SLA printer. Now, an SLA printer is a 3D printing method where you're building up the part on out of the SLA. And basically you just do it layer by layer, and you come out with a plastic part at the end, which you then clean up and prepare. So basically what you see on the left-hand side is 16 of the chassis bodies, the satellite chassis body coming out of the printer. So basically one of the things that we're able to demonstrate with this is that, well, without having tooling, we can print off around about 16 of these a day. And that gives you some idea about what the potential size of batches is going to be. On the right-hand side, you can see one of the SLAs which is cleaned up, and I still have some of these. I have one here, but you can get a feel for the size of it. They're not big. You know, they're sort of, again, this particular one's around about 10 centimeters on the end and around about 20 centimeters long. It's got some flat sections on it that you see here, which were meant for mounting onto a flat panel, and but you can see the general geometry of it's pretty complex. It's just very, very open, and so that's what we were looking at casting. So the tree assembly. So basically, getting metal in was going to be a challenge all the way along. Now SLA, it doesn't behave exactly the same as wax, so we had to account for the particular idiosyncrasies of the SLA and also for the wax. On the left-hand side, you can see the part where it is in the wax tree. The green part is wax, the SLA is the white section. On the right-hand side, you can see these are vents that are being put in. Now, the vents are there for two reasons. One is to get the wax out before you flash fire it. The other is that when you flash fire it, you've got to get lots and lots of oxygen in so that you can burn off the SLA pattern very, very quickly. There's also some small vents which you can see here on the thin sections. So this is the shell being built, and it's going through the drying process here on the hangers while it's being dipped and dried. On the left-hand side, you can see it's building up. That's after probably 2 or 3 coats. On the right-hand side, getting close to the end of the process of putting on the backup coats on the ceramic shell. So this is starting to get close to the final stage of actually making it. So here, the next thing, you open up the vents on the left-hand side, open up the vents, remove as much of the wax as you can with a hot air gun, burn it out, and you can see the middle one is the burnt out part, where all the vents have been broken, the ceramic's been broken off to open the vents. And then on the right-hand side, where where the shell's being reinforced. Now, sometimes you reinforce the shell because you have some cracks may appear in the shell. Other times you do it just to give mechanical strength in the shell as well. And so here the vents are not being closed off, that you can see here, these little thin vents, but the shell is being reinforced before doing that particular part of the step. One of the reasons why you have these as well is so that you can blow forced air down into these areas to get any ash or residue that might be in there and actually blow it out so that it can be removed. So this is so the shell is then preheated. You prepare your metal and cast it. All of this part of it now becomes pretty routine, pretty straightforward. On the left-hand side, you can see it straight after casting, and you know, it's always one of these things with investment castings. We get the ability to take a photo of the part while it's starting, just after it's been cast, so we get the ability to see what its thermal profile looks like while it's cooling down. And you know, so that gives you a good idea about whether or not you're right on the right path, of course. So you can see it's end on here and then side on here, very similar to what you saw in the wax stage earlier. In this, now it's at the point of being cast and ready to be cooled down and have its shell removed. So the first step that happens is water blast. So you remove all the ceramic shell with forced water, with high pressure water, and you can see that the part is inside the runner system here, and held quite firmly within the runner system. Now that is something that we learnt was extremely important. The reason being, and the reason why I've put heat treat in the middle here, is that you actually must heat treat these parts with them while they're still on the tree, just because the walls are so incredibly thin. Basically, there is no structural strength at high temperature when you're only at 1 millimeter or so. So if you want your casting to not move around too much, you've actually got to heat treat it with it still actually attached to the tree. So you heat treat it on the tree, and then once it's off the tree, take it and fettle it, cut it all off with a abrasive cutoff wheel. You can see the cutoff wheel on the right-hand side there as we're removing the runner system. And so then we end up with the cast parts. We clean them all up and take them and machine them. And you can see the first 3 chassis that were cast, the first 3 satellite chassis that were cast here, all fully machined, all machined at our machine shop. We had to learn how to machine this material as well. It is very, very gummy, a lot like very soft 316 stainless. So you tend to form very gummy chips, and you have to be very careful while you're doing it as well, of course, because of that fact. But so we developed all the machining procedures as well that would be required for doing the stuff that was required for this. Now, basically, the machining was pretty straightforward. It was basically after the casting was fully straightened, facing these sections off so that the panels could be bolted onto them. And then drilling and tapping some holes into the 3 main bosses that were there so that the internal hardware could then be put into position and placed ready for the next step of the process when after we ship them to our customer. So this is the guys who helped me in the foundry do all of this, and so you can see the actual size of these parts again. They are quite small. And so, you know, very, very appreciative of all the help I got from the AW Bell team, from the wax room through to foundry, aftercast, and machine shop, and our management. Everyone contributed very, very well to this project, and it was a great outcome all round. And you can see when the proof's in the pudding, I still have one of them here. So this is the Invar casting, of course, which is the same as the one that you see in the picture. But that gives you some idea of what we're looking at there. So in conclusion, Invar may be successfully cast using standard air melting techniques. The material is particularly sensitive to the presence of silicon and manganese, which contributes to hot tearing. The alloys are surprisingly less sensitive to increases in carbon content. We found that nickel offsets the inflection point and Curie temperature to higher values, but does not necessarily impact the castability. The thermal expansion may be tailored to match window materials such as borosilicate glass or sapphire. Although we haven't been asked to do that at this stage, we did find that to be feasible. The material has quite an extraordinary fluidity, and you can achieve wall thicknesses down to around 1 millimeter in an investment casting. The mechanical properties that we looked at for the materials. All of the mechanical properties we looked at for the different nickel specifications met the requirements of the ISO standard for the alloy GX3 nickel 36. And we were able to demonstrate commercial feasibility for printing cube satellite chassis direct from CAD data into SLA, and then investment casting these into Invar. So with that, I'd like to thank you all very much for listening to my talk, and I'd say we're ready for some questions. Thank you.
Thank you very much, Roger. Great talk. I'm going to handle the questions, and Amber will wrap up.
Sure thing.
After we've exhausted it. I haven't seen anybody typing in questions in the chat box. So if you do have a question, I guess one way to do it is unmute and start talking. Somebody's come up and said, why choose SLA?
Okay, well, SLA was chosen because this has been pretty much a standard product for investment casting for some time. SLA has been the material of choice for using 3D printing methods going back quite some time. I mean, our SLA machine probably goes back to around about 2010 or thereabouts. Before that, we were using other methods like FDM and a few other various methods, wax printing and the like. SLA gives you very, very good surface finish, around about 0.1 millimeter in terms of the ripple size that's on the surface. Gives you very good structural stability in holding the shell together as well. We have been trying some other materials. And say, for example, you can use some other plastics. They're not too bad, but generally SLA is extremely good for a production facility when you're making one or two at a time.
Thank you, Roger. Sam's asked which welding process is commonly used for Invar.
It's generally TIG. It's quite easy to TIG weld.
And easy to get the filler material or anything? That sort of stuff?
You have to buy the right filler material. I bought the there's a supplier that we have in California who can get me almost anything I want for filler material, and so I asked him for it and he found it and was able to get it to me before I needed it. So it was all good.
Handy to have a global network you can call on.
Yeah, well, I mean, someone in California, they're actually not on a bad time frame for us, so you can actually get on the phone and talk to them, of course.
Mm-hmm. Yeah, we can do that with Europe too, but if you've got to communicate with all of them, both Europe and the US, you're in trouble. You never sleep.
Yeah.
So Admos has asked if you were going to full production, would you tree up multiple parts, 2 to 4, for better yield?
I think if you could, yes. I think Admos is saying that because he's a foundry supervisor, of course. So, so of course he wants to make sure he's getting the best economy out of his metal he possibly can. But yeah, I think it's tricky. The treeing part of it is quite complex, and I think you could do 2 because basically we used one side of the tree to cast the part. So there's no reason why you couldn't use the other side. And I mean, going to 4 would be quite difficult, but not impossible. All these things are certainly possible if you're willing to put the time into it.
Okay, somebody, Alan's asking, what does moly do to Invar? Okay,
well, this is a very, very interesting question, and I never realized how important moly was, and still, we often look at 304L, for example. We make 304L, we cast it. We cast 316L, and it's got moly in there as well. It turns out that moly has quite a pronounced effect on fluidity of stainless steels, and it seems to have quite a pronounced effect on fluidity of other steels as well. Now, you don't need much in there to make this happen, but it has a noticeable impact. The biggest advantage of it really is that usually we'd add things like carbon, silicon, and manganese to improve our fluidity, especially carbon, because that has a massive impact on fluidity. But what you can do is you can drop your carbon right down to very, very low levels and put a little bit of moly in there, which has less of an impact. So you can trade off the negative impact of carbon by having the bit of moly in there to sort of account for improving fluidity of the material. At least that's what I've noticed, at least.
These things are so small, and like you said, I think the future is they're just going to throw lots of these up there. And so what's the market for this per year?
Well, I mean, if it's at the moment, it's growing at a extremely fast rate. Now, in the Australian context, we of course have a new space agency, and their focus is going to be on cube satellites. There is also, you look at the likes of Honeywell, Northrop Grumman, a lot of the big aerospace companies that are already manufacturing satellites. And you put the word cube satellite in front of their name and look at what they're doing, and it's quite extraordinary. The likes of Honeywell are looking at making thousands and thousands and thousands of these things over the next decade or so.
So you investment cast it. How do other people manufacture these? They don't machine it out of a billet. Please tell me they don't do that.
Oh, it's not. It wouldn't be clever to do it that way. So, quite often they are. Currently, they're still struggling with using. They're still struggling with using machined aluminium for a lot of it, and so they're trading off the sensor drift for thermal for using lightweight materials, which is completely valid, except when your sensors are going to be very, very sensitive to thermal drift. You know, I mean, the way a camera works is that, or the way a sensor works is that you can either use a very, very expensive sensor that calibrates itself, or you can use a dirt cheap sensor in a frame that doesn't move around. So, you know, there's a big advantage in having this low coefficient of thermal expansion. And, you know, a part like this, I would say this is around about, it's about 2 kilos by the feel of it. So I do have, I just can't remember the weight on it. I haven't written it on it, but it's only about 2 kilos or so.
Alan Cook made a comment. I think Elon Musk is planning to put up thousands of these things and give us cheap internet. Maybe it'll be better than NBN, which we all struggle with.
Yeah, well, the principle of when they work in large numbers in constellations, the principle is that if you put up 100 of them in an array, it has an enormous coverage. But if one of them fails or goes down or gets hit by a bit of space junk or something like that, the array still operates completely, or basically at 100% functionality. So it's that built-in redundancy that I think is very, very appealing to the companies that are looking at them.
Alan seems to want to ask lots of questions.
That's all right.
Its orbit, is it a low altitude one? And what happens when they drop back into our atmosphere? Well, they'll probably burn up, and they might land on your place, Alan.
Well, the orbit where most of them are currently being used, they're doing a lot of work and looking at what's called the thermosphere, which is a little bit further out. I think it's about 100 kilometers out or so. And currently they're doing studies in that range. Now, of course, in future we may expect to see them at lower heights, and that would be completely expected. So yeah, I mean, the issue about what happens to them when they've reached the end of their life is certainly a very, very important one. And I think that because of their size, they're basically most likely to burn up pretty conclusively when they re-enter the atmosphere.
Alan making another comment. There was a program on TV last week all about this. Was that about what you guys did? Is that what he's talking about?
I didn't see the program.
Okay.
I went looking for. Alan mentioned it to me a week or so ago, and I went looking for it, and I couldn't find it. So I'll have to get in touch with him and see if he can tell me exactly what it was.
Yeah, maybe Alan watches too much TV.
Well, there's not a lot else to do, actually.
Chris is giving you a compliment, saying excellent work and a real credit to A.W. Bell and yourself. So well done.
Thank you.
A.W. Bell is renowned for doing excellent work, so you're keeping it up.
Yeah, thank you very much.
Maybe we should draw this to a close. We've gone a little bit longer than we anticipated, but close. if anybody else has got a question, you better be quick. Alan wants to get in another one.
Yep.
How long did the project take?
Okay, we started late. We were supposed to start in November of 2018. We didn't get started until January of 2019, and all deliverables were delivered on time by the end of May.
That's pretty good.
Yeah. So less than 6 months.
All right. And Barlow's congratulating you too, saying great work and well done.
Thank you, Barlow. Yeah, I think one of the things when I first wrote the project proposal on this, it was very pointedly made it being a 6-month time frame to do it. I think that the reality of it is that we talk about innovation cycles with projects and the like, and most innovation cycles they're getting so short. We really have to be able to deliver within 6 months or so. Now, we had to deliver within 6 months to be able to enable University of New South Wales and CSIRO to hit their targets. So we had to get our chunk out of the way before everybody else. So we had to be able to really hit the ground running and deliver on time. And also, I was going overseas to Europe for a month, so I wanted to get it finished before I left.
It's a good incentive. I think I remember those days of travelling. That's sort of long gone.
Yeah.
All right, so thank you very much. I'm going to hand over to Amber now. And Simon said, excellent work. So everybody's giving you congratulations. How about we call that it for the questions and comments? And over to you, Amber.
Great, thank you. Thanks again, Roger, for your presentation and taking us through so thoroughly the steps and the processes you went through during this project. We really appreciate it, and quite clearly everyone enjoyed it and got a lot out of it. In 2 weeks' time, we are lucky and pleased to be able to present Professor Matt Barnett at our next SOFA seminar, and he's going to be talking to us about some creative applications for the circular economy principles, followed in another fortnight by a presentation from Professor John Campbell, who is with us. Thank you very much for joining us tonight. Who will be sharing some information and practices on how to greatly improve your casting quality and also at the same time reduce cost. A fortnight after that, so on the 21st of October, the final SOFA seminar, also presented by Professor Campbell, we'll be sharing some information on engineering developments associated with vast improvements and failure elimination in casting. So on that note, I just want to remind everyone, if you know of someone who didn't manage to make tonight's presentation or you'd like to see it again, please, in the next couple of days, go to the AFI website. This presentation will be uploaded on the Victorian page and in the folder AFI On Demand, because we're just taking it to the nth degree, this whole virtual reality and the presentations for you to access at any time. Thank you all again for joining us. We hope that you have enjoyed this presentation as much as I know I have, and I look forward to seeing you all again in 2 weeks' time. Thank you very much.